Okay, let's do a little excursion into, first we need to figure out if Newton's universal law of gravitation is a conservative force, and then can we find a potential energy function for that? And then I want to talk a little bit more generally about, we've talked about polar coordinates as a different coordinate system and cylindrical coordinates. I'm now about to introduce spherical coordinates, and I want to kind of venture a little off topic and talk about kind of general curvilinear coordinate systems, so things that can go beyond Cartesian, and how all of these different coordinate systems actually are just examples of this more general thing, which actually comes up a lot in differential geometry and general relativity and special relativity, which we won't use and need, but I thought it'd be fun to introduce the idea a little bit. So let's first start with Newton's law of universal gravitation. And the way I've written it down is that there's a big mass m that is, I'm going to put stationary at the origin, and it is attracting the little mass little m, or the mass little m, towards it. So there's a force on little m from big M, and that universal law of gravitation force can be written as negative g big M little m all over the position vector squared. Really, it's the relative distance between the two, but I'm going to simplify things and keep the big mass at the origin and let it be stationary. And the negative sign is because it points in the opposite direction as the position vector, because it's an attractive force. So in this case, this is an example of a central force, or a center-seeking force. And most books dedicate entire chapters to kind of studying the properties of forces that are these kind of center-seeking forces. Let's just look at a few of the properties here with Newton's law of universal gravitation. While this is written as, it depends on the vector position, this particular force, if you look at it, really is only a 1D function, not of the vector r, but of the magnitude r. Right? If you tell me the magnitude of the position between you and the object, then I'm done. I can tell you the magnitude and the directionality from that more or less alone. So this really is a kind of 1D, even though this can be true in kind of a three-dimensional space, this is in a sense a 1D function, and that the only one dimension that matters is the dimension connecting the two objects. If I draw a line between the two objects, that axis is the only dimension that really matters. So if we put one of the masses at the origin, that line connecting the two objects is always pointing in some direction radially outward from the origin. But since it can be located kind of anywhere in the XYZ domain, spherical coordinates might be more relevant here, because it's not really a cylindrical problem in that, where you have kind of circular motion in two of the dimensions and then kind of Cartesian in the z direction. Really, it's, this the radial component that matters, but then anywhere along that sphere that has the same radius is feeling the same magnitude of the gravitational force, and the direction is always kind of pointing radially inward. So to study this, spherical coordinates will be useful. Now, how can I motivate this? We have a general position vector, x, y, z. Like what we did for polar coordinates, we want to find a way to map x, y, and z onto a new set of three orthogonal directions that are going to correspond to the three axes in spherical coordinates. So let's see, for Cartesian we have x, we have y, we have z. And then let me use a different color. I have some general position vector that goes out to x, y, z. And so what axes am I going to use in this case? For polar coordinates, we had the radial, and then we had the tangential, and then we added in the z for cylindrical. For spherical coordinates, we're going to use, again, the radial, but now this is kind of a three-dimension radial. So I'll use r hat for that case. So there's the radial dimension, the direction that always points away from the origin. That's going to be one of my axes. Don't like the thin line. We redo that and be nitpicky here. So we got this, which I'm going to call little r hat, which is radial. And then, again, by the right-hand rule, I'm going to want to try to find two other perpendicular axes that have some sort of cyclic relation amongst them. So one of the axes is going to be the altitude angle. So it's going to be pointing in this direction, and it's going to be defined by the direction theta, which is the altitude angle. And that's going to correspond to a particular angle, the angle that this vector makes with the z-axis. So how much are you moving from the z-axis, where I could rotate around this way? That's not changing the angle you're making with the z-axis, right? This angle here is going to be one of the parameters that define your position in x, y, z, or in spherical coordinates, and then we're going to need to translate them into x, y, z. And these are going to be defined to be perpendicular to one another, of course. Now, if I imagine the shadow that is being cast by this blue dot, right, the shadow might be cast here, in which case the vector itself has a shadow in the xy plane that points out in that direction. And so there is another angle that I can define to help me kind of locate this object in three-dimensional space, and that is this angle here, which I'll use as phi, which is kind of very similar to the tangential angle we had for polar and cylindrical coordinates, because it resides in the 2D xy plane. But then there is going to be an axis associated with that angle, and that one is going to be a little hard to draw because it's in the way I've drawn this is kind of more pointing into the page. Oops. Or tangential azimuthal is another word that would appear. And it's kind of pointing into the page, so if I try to draw it, right, it's also making kind of a 2D angle there, and then it's making a 2D angle, 90-degree angle there. So we got kind of three axes that are all perpendicular to one another. Kind of got the radial direction, the tangential direction, and I guess and then the altitude direction, and kind of the way I've drawn it there. So these can define your three parameters. So in spherical coordinates, your variables are r, theta, and phi. How far away are you from the origin? And then the two angles that you can make relative to the z-axis, and then the projected, what angle you're making relative to the x-axis when you project into the 2D plane. And so in this case, there are conventions where the theta value can range from 0 to pi, where phi is allowed to range from 0 to 2 pi. And again, that's so that every point in the three-dimensional space is defined by one unique, triplet of r, theta, and phi. If I let both of those angles range from 2 pi, right, I can imagine, right, there's some point here where if I imagine towards the camera corresponds to, right, some given I don't know, some given phi value. Let's call this phi equals 0 perhaps. Right? I could, point it towards here, and there's some coordinate. But if I allowed this thing to go kind of around 2 pi, so that my altitude could ultimately point the arrow in the opposite direction, then I could also rotate my phi by 180 degrees, and that would be pointing to the same spot. So it's possible you would be double counting certain regions if you allowed both to go from 0 to 2 pi. If you allow only one to go to pi, you can uniquely determine every location in 3D space by a unique set of 3 numbers. And if we want to think vectorially, these angles, or these unit vectors, also obey the cyclic relationships we talked about before, where if I take r and I do the cross product with phi, again by the right hand rule, start with r, go down to phi, my thumb points start at r, go to theta, my thumb then points in the phi direction. If I do theta cross phi, I get r, and then if I do phi cross r, I get theta. So these have the same cyclic relationship that we had for cylindrical coordinates and polar coordinates, and that we have for the Cartesian coordinates, right? X cross y equals z, y cross z equals x, etc. So now we need a mapping to go from Cartesian to spherical. And that's not too bad if you look at the drawing. So the easiest one probably is z, where there is, in order to get, if I have a certain location in spherical coordinates given by r, theta, and phi, how does that translate to a z direction? Well, there's a 2D triangle already that I can use, and it looks like, writing x, y, z out of order, it looks like z is then just going to be r cosine of theta. And that gives me a z component. To get the x and y components, I have to first project myself down into the xy plane. So then that gives me the shadow. And the shadow, again, by the same, there's another triangle here. Let me highlight it. Right, there's this triangle here, where, again, by the rules of right triangles, the shadow has length not r, but the shadow has length r sine theta. And so then if this is now my new hypotenuse that has length r sine theta, I can project it into the x direction and into the y direction to get the x and y components. And so then that just says x is kind of that r sine theta, and then it looks like this is multiplied by cosine of phi, and then y, you have the r sine theta, and then you have the sine of phi component. And that gives you the relationship between the two. And if you want to write in terms of if I'm given x, y, and z, how do I get r, theta, and phi? Well, then r is just given by the Pythagorean theorem. Looks like theta, right? If theta looks like, if I know z and r, I'm pretty good. So if I first calculate r, then I might do inverse cosine rather of z over r to get theta. Then phi, I could use the triangle that's projected into the xy plane, and it looks like that's going to be inverse tangent of y over x, which gives you a way of going back and forth between the two. Now, remember, like polar coordinates, these vectors are going to change when they undergo time derivatives. And for polar coordinates, it actually was useful to write down position vectors, velocity vectors, acceleration vectors, which again you could do for spherical coordinates as well. I don't think we actually will ever need to do that, but you could, right? If you wanted to do F equals ma and you wanted to use spherical coordinates, right? You could write down all the forces in the r, theta, and phi directions, but then the acceleration vector you use would not just be simply, x double dot like it is for Cartesian, but it would be some slew of terms like it was for polar coordinates, where it was like r double dot minus r theta dot squared for the radial direction, for example. This means, however, to get back to the ultimate question that we were trying to figure out of, is this a conservative force? Remember, to ask ourselves if something is a conservative force, I need to evaluate the curl of that force and ask, is it equal to 0? To do this in Cartesian coordinates would be very, very challenging, because f in Cartesian coordinates is negative g, big M, little m, over r, and then this whole thing in the bottom is x squared plus y squared plus z squared. And then r itself is also a function of x comma y comma z. So taking the curl of that with all these partials with x and y and z, it can be done, but it would be a little challenging. So the question is, can I write this in spherical coordinates? Which can't simply be the same thing, but you replace all the partials with partial r, partial theta, partial phi. Right? There has to be a little bit more to it because the unit vectors are changing under time, when you have derivatives going on. In this case, there's no time derivatives, but nonetheless, you still have to be careful about how things are changing in space as you move around space. And so you might have derived some of these in a calc class, but then you have relationships like this, like the ones that are given in the back cover of your book, where when you are trying to do div, grad, and curl, and also the Laplacian, which is the divergence of the gradient is the Laplacian, that it's not quite as simple as it is for Cartesian, but additional kind of things pop out, like sometimes there's a 1 over r or 1 over sine theta. Cartesian's kind of the usual determinant for curl, but for spherical coordinates, notice there's some sines and some r's all popping out as well that you have to take into account. So let's use that as a given now, and then kind of generalize this a little bit later. So using your book, or using kind of a table lookup, you can see that the curl in spherical coordinates is 1 over r squared sine of theta. And then there is still a determinant, but it's a little bit more complicated, right? The top line is not just the unit vectors, but it's r hat. The second one is r times theta hat. And then the third one is r sine theta phi hat. The second line still is the partials, partial with respect to r, partial with respect to theta, partial with respect to phi. And then the bottom, in this case, is the 3 components of your force vector. So since this force vector only works in the radial direction, that's nice because that makes these two terms 0. And then this then is going to be negative g big M little m over r squared. And then if I can compute this determinant, that is my answer. And so this looks like it's going to be pretty easy, right? This direction, derivative of 0, fine. Here, derivative of 0, fine. Here, the phi derivative of that expression, which has no phi in it, so that derivative is going to be 0. And then this involves a derivative of 0. Then I got this multiplied by a derivative of 0. And then this involves me taking the derivative of this expression. But again, that expression doesn't depend on theta, so that's also going to be 0. So in this case, indeed, this looks like this will result in giving me a 0 vector. The curl does indeed vanish. So I know, therefore, there is a potential energy function that I can write down and can evaluate in this case. Well, the potential energy function, which again is defined as negative from some reference point to some arbitrary point of this force vector dotted with some dr, where that dr is some path that takes me from my reference point to some arbitrary point. I need something for dr, which again will motivate where this comes from, but dr in this case is not just dx, dy, dz, but it's dr, r d theta, and r sine theta d phi in spherical coordinates. And I think these are also written somewhere in the covers of your book. If not, it's on a handout I'm about to make available to everyone. And so in this case, it looks like the potential energy is negative this integral, and it's negative g m little m over r squared dr. And that is it. I'm going out to some reference point, which it looks like in this case, there's no theta and phi, so it's going to be out to some arbitrary r radial location. This is essentially now just a 1D integral. But I need a reference point. Notice how you can't use the origin in this case, because if you use the origin, that would be requiring you to plug in 0 in the denominator. So in this case, the origin can't be the reference point. So the convention is to actually use infinity as the reference point, or a value of r that is so absurdly large and far away from where all the action is happening. So in that case, it looks like this ultimately becomes the negative signs cancel, but then I integrate a polynomial with a derivative. So this looks like it's negative g big M little m over r, ending at r and starting at infinity. So coming in from infinity to your location. And it looks like in this case, then I get negative g m little m over r, because then I'm subtracting from that something where the denominator is infinity. And this is for Newton's gravitational force effect. Let's see, it's probably worth a highlight. So ultimately, the potential energy is negative gmm over r, using the convention that infinity is where we're saying this particular potential energy vanishes. So you might not think that that was an easy way, but that was much easier to derive using spherical coordinates compared to if we stuck with Cartesian. And now we can use this, again, in whatever coordinate system we want. So if I'm just throwing a ball up into the air, I can still use, or even though that's kind of a purely 1D vertical, I might think of it as the y direction, I can still use then Newton's universal law of gravitation in that case too. So this is useful when you're dealing with gravity, but it's not a constant gravitational field like near the surface of the Earth. This is what you would be using if you wanted to deal with, say, the kinetic energy of the Earth as it goes around the sun, right? It would be this negative gmm over r, where it would be g, mass of the sun, mass of the Earth, over the distance between the Earth and the sun that you would plug in. The kind of subtlety, and we won't have to worry about this too much, is that this is defined technically for a pair of objects. Notice there are two masses in the problem. So, this potential energy is the potential energy associated with the gravitational interactions between the two objects that are tugging on one another. So if you had, for example, 3 objects in your system, and they're all kind of roaming around via their kind of mutual gravitational interactions. Maybe M1, M3, we'll call that R13. The distance between M1 and M2, we'll call R12. The distance between M2 and M3, we'll call R23. If you wanted to write down the total potential energy for these 3 objects, there would not be, we could ask how many terms should we expect in this case, knowing that the potential energy is defined for a pair of objects. So in this case, U total would be the potential energy associated with 1 and 2, plus the potential energy associated with 1 and 3, plus the potential energy associated with 2 and 3. The 3 possible interactions that can go on in this case. So it might be something like negative M1, M2 over R12 minus G M2, M3 over R23, and then minus G M, I guess I skipped 1, 3. G m1 m3 over r1, 3. That would be the total potential energy for a 3-body system that you would have to take into account. It's a small subtlety. Useful for me since all my stuff is astrophysics, but something to remember and keep in mind. This really is defined for a pair of objects. Okay. But I wanted to talk a little bit about these kind of curvilinear coordinates in general. So this is kind of a brief excursion into differential geometry. Differential geometry, which comes up particularly in general relativity. Where it is getting towards you being able to have an arbitrary coordinate system. We're talking about things like where you have Cartesian coordinates, where everything is kind of flat sheets of paper in the x, y, and z direction. Polar coordinates is kind of, you can imagine the universe as a big cylinder, or spherical coordinates where you're kind of measuring everything on kind of a big globe. But take, for example, kind of the iconic pictures you've seen of what does space-time look like near a black hole, right? You might have space-time that's kind of generally flat, but then near the black hole, there's some big dip in space. It's kind of a 2D representation of a warping of 3D space-time, where if you were to lay down a grid of what this looked like, right, out here, the grid is kind of flat. It might look kind of Cartesian-like when you're far away from the black hole. But near the black hole, the curvature of space starts to become a little bit more distorted, so the grid cells might not look like nice little Cartesian squares. And it might start to kind of loop around and look something that's kind of circular or spherical, or it might be some other arbitrary shape depending on kind of what's going on and how space and time are being warped. In that case, you have a coordinate system where as you go from regions of space to the other, your coordinates are in a sense transforming, so that it might be Cartesian at this step, but then you take a step over and it's something that's not quite Cartesian, and then you take another step and it becomes even more distorted from Cartesian. And so differential geometry is kind of the ultimate generalization of all of this, where you can have a coordinate system where the coordinate system itself can be changing arbitrarily, as you move around 2D space in the case of the drawing I just made, or 3D space, or 4D space if you're doing space-time. And string theory, 11-dimensional space and all that fun stuff. So obviously we don't need to get that sophisticated here in classical mechanics, since we made the assumption that relativity and general relativity aren't a thing. But the mathematics that Minkowski and Einstein and Christoffel and Ricci and a lot of mathematicians developed, on the subject, do kind of more give a sense of more of a general flavor of what's going on with coordinate transformations. And so let me motivate with Cartesian as a start. Cartesian. The position vector is given by x, y, z. A change in your position vector is then just dx, dy, dz. Pretty simple. And there's a particular invariant, as it can be called in differential geometry relativity, of dr dotted with itself, or just dr squared. This actually plays a very important role in these kind of general differential geometry space-times, sorts of analyses. Where in Cartesian coordinates, this looks like it just becomes dx squared plus dy squared plus dz squared. So again, or you can think of that, what is the arc length? How long is this little bit of dr? Well, it looks like then it's the square root of this distance here. And again, that kind of motivates why this is important, because if I'm taking some path through some sort of constantly deforming space, my path length is then going to depend on kind of how the deformations in each of the three dimensions might be changing, right? In this, for Cartesian coordinates, there's essentially no deformation in any direction, so it just depends on how much in the x, how much in the y, how much in the z I move, and that can tell me the length of my path. But if things are changing along all the while, right, it might be that it's not just dx squared plus dy squared plus dz squared, but it might be some function times dx squared, plus some function times dy squared, etc. So there are a couple terms which we've seen already. So in this case, notice there are no cross terms in dr squared. And by that I mean there's no, right, there's a dx times itself, there's a dy times itself, there's a dz times itself, but there's nothing like a dx times dy or a dy times dz. So if you move a little bit in the x direction, you don't also have to multiply that by any sort of motion you have in the y direction or in the z direction. This mathematically is what we mean by orthogonal. Is that when you evaluate dr squared, you don't have any cross terms. Which again, what that is saying kind of physically is that if you move a little bit in each dimension, and one dimension at a time, you don't have to take into account what's going on in the other dimensions, right? It's not that you, by taking a step in dx, you don't also take some sort of step in dy or dz. If you take a step in purely dx, you take a step in purely dx, and that is not influenced by y or z. So we call that orthogonal. When there are no cross terms. And the problems at the end will give you an example of a non-orthogonal system. There's also, with Cartesian, has no spatial deformations. And by that I mean there's nothing in front of the dx squared, the dy squared, the dz squared. I could write this as, and the way it's generally written is that dr squared is the number 1 times dx, and that's all squared, plus the number 1 times dy, that's all squared, plus the number 1 times dz, that's all squared. Where these ones are called the scale factors. Of Cartesian coordinates. And again, Cartesian coordinates is relatively simple. So there's no kind of deformation that you have to worry about as you move in every dimension. Just to jump ahead a little bit, that is different for, say, polar coordinates, where if you move a little bit in the radial direction, that's fine. But if you move a little bit in the theta direction, right, how far you move, if my finger is here, is smaller than the amount of distance I move for the same kind of delta theta, when I'm at the tip of the pen. So how my path length, my little dr, if I'm moving in theta, that does depend on the exact distance I am away from the origin, in order as I trace out that path. So I might expect that there is a scale factor there, and in that case it's just the value of the radius. Let's just do that now as an example. So for cylindrical, And this is kind of the approach in general of how you can calculate these things, because ultimately, if you know the scale factors, which again for Cartesian was the scale factor in the x direction, which is 1, the scale factor in the y direction, which is 1, the scale factor in the z direction, which is 1. Turns out I'll show you that if you know the scale factors, you can figure out all the div grad curls and all, and what's a differential volume element if you're doing a volume integral. It's essentially just a multiplication of all these scale factors. So let's take cylindrical coordinates. That's kind of easy to do, and it's easy enough to do the math to see how this works. In that case, you're going from x, y, z to the new variables r, theta, and z, if we're sticking with 3D. And all you need to write down is the transformation. So x is r cosine theta, y is r sine theta, and z is just z in cylindrical coordinates. It sticks with the same Cartesian. And so to compute the scale factors, ultimately you want to compute, again, you want to compute dr dotted with dr. So we want to write dr first in polar coordinates, and then when we take the dot product, we can see, do we get things that look like this with these, are there cross terms, and what's going on? So the first step, if you have a transformation that tells you what x, y, and z are, you can then compute what dx, dy, and dz are. In terms of your new 3 variables, r, theta, and z. So in this case, it would be dr cosine of theta minus r sine of theta dr. dy would be dr sine of theta plus r cosine of theta. Sorry, this should have been a d theta. D theta. Z then just becomes dz. Now, with that, I can compute dr dot dr, which again is dx comma dy comma dz dotted with itself. But now, instead of doing dx, dy, dz, I'm going to replace it with, it looks like it's cosine dr minus r sine d theta, comma, sine theta dr plus r cosine d theta, comma, dz, dotted with, and then repeat that. So then the math is a little bit more involved, because then it looks like at the end of the day that dot product is cosine theta dr minus r sine theta d theta all squared plus sine theta dr plus r cosine theta d theta all squared plus dz squared. And then I have to multiply all these out. But we can just look at the, let's just look at the first term, right? So there'll be a cosine squared times a dr squared. Right, so there'll be cosine squared dr squared. There'll be a r squared sine squared d theta squared. And then there's going to be the cross term 2r, looks like sine theta, cosine theta, dr d theta. And that's just expanding out this. Gives you these 3 terms. Then I could do the same thing for this, and then I could do the same thing for this, and I'll let you fill in the blanks. These cross terms, it turns out, end up canceling out. And at the end of the day, also remembering that cosine squared plus sine squared equals 1, you end up at the end of the day getting something that looks like dr squared plus r squared d theta squared plus dz squared. And here I had to use the Pythagorean identity as well. when I was doing this proof. So then at the end of the day, it looks like this is 1 times dr all squared plus r times d theta all squared plus 1 times dz all squared. And we have identified the 3 scale factors. Well, one, we've figured out that this is an orthogonal coordinate system because there's no cross terms left over at the end of the day. There's no dr times d theta. There's no dz times dr. All those went away. And in this case, we can find that the scale factor in the radial direction is 1, scale factor in the theta direction is r, and the scale factor in the z direction is also just 1. For spherical, again, I'll let you kind of fill in the blanks. You can do the same sort of approach you did before. And we wrote down what x, y, and z are in terms of r, theta, and phi. And you end up getting 1 times little dr all squared plus little r times d theta all squared plus r sine of theta times d phi all squared. So in this case, the scale factors for spherical coordinates is 1, theta is r, and for phi it's r sine theta. And in the description, there should be a link that also kind of summarizes all of this. And that will also be made available for those in class. But let's see, let me see if I can bring this up without giving away everything right away. All right, so if I bring this over here, we've kind of defined these scale factors as the thing that's in front of, like in this case, the number that's in front of the dr, the d theta, the d phi, and those become the scale factors, which I'm generally calling h. For a particular coordinate system that's orthogonal because there's no cross terms. And just summarizing what I'd written out earlier, we had shown that for Cartesian, the values are just 1, 1, 1. For cylindrical coordinate systems, it was 1, r, and 1. For spherical, is 1, r, and r sine theta, were the 3 scale factors in this case. Now again, the absolute nice thing, which again we can just take the result as a given from differential geometry, is that in general what this shows, and if we look at, let me move this out of the way for a second. In general, what is going on is that we can very generally start asking ourselves questions like, what is my little, let's see, let's make sure I can have both things that I want on the screen. For example, what is the vector dr in any arbitrary coordinate system? Well, it turns out that the answer is just that it's the scale factor in that particular direction times kind of whatever the dx is in that direction, and then plus the unit vector, plus it's 3 dimensions. Oops, I skipped to dx, and whatever the dx is in that direction, and then in the 3rd direction. Where here I'm using kind of subscript notation. Everything is an x, but I'm using subscript notation. So for Cartesian, right, it was 1 dx in the x direction plus 1 dy in the y direction plus 1 dz in the z direction. So that the vector at the end of the day was dx comma dy comma dz. In cylindrical, the radial, or if we bring it back, the radial scale factor was 1, so it's 1 times dr in the radial direction plus Now the scale factor is r d theta in the theta direction, and then this looks like it's 1 dz in the z direction. So it looks like then this little position vector is dr, r d theta, dz. For spherical coordinates, write 1 dr in the r direction plus r d theta in the theta direction plus r sine theta d phi in the phi direction. So again, then it looks like it's dr, r d theta, r sine theta d phi. And again, just by kind of the general relationship of dr is just the product of scale factors, the differentials in each direction. Now similarly, like what's on the screen, a volume element, if I want to do a volume integral, is just the product of the scale factors times the product of the differentials. And that's true in general, no matter what the coordinate system is. So again, in cylindrical, in Cartesian, it's 1 times 1 times 1, dx, dy, dz, or just dx, dy, dz. In cylindrical is 1 comma r comma 1, dr, d phi, dz, or just r, dr, d theta. Sorry, I keep saying phi. D theta dz. In spherical, 1 times little r sine theta, dr, d theta, d phi, or it becomes r squared sine theta, dr, d theta, d phi. And if you're doing an area integral, then it's just the product of the two dimensions that you're integrating over, right? If you're integrating over, say, a shell, that suggests spherical coordinates, but if you're integrating over a shell, then the value of r is not changing, so there's not going to be an integral over r at any point, because r is just going to be a constant over the shell. So in that case, I would say it's h theta h phi times d theta d phi for your differential area element, which in that case looks like it's then going to be r squared sine theta d theta d phi as a result. Which again, very, very nice, because essentially then if you want to remember anything, you can just remember these very general expressions, and then you have to just know what the scale factors are. And then last but not least, and I don't think I'll write these out because they get very complex, is that you can do the same thing for div, grad, and curl, and that the vector operations can be similarly summarized, where if I want to take the gradient of a scalar function, I can very generally just write it out as this: 1 over the scale factor, the partial with respect to the first thing, which might be x, might be r, might be little r, depending on your coordinate system, 1 over the scale factor for dy or d theta or d theta, 1 over the third scale factor, partially with respect to z or phi. Similarly and then these get a little bit more involved, but you can write down a very general expression for the gradient, the divergence, the curl, and the Laplacian. And so in spherical coordinates, for example, I go through the example of, for the gradient, the scale factor for h1 is unity, so it's 1 over 1 partial with respect to r in the r direction. The scale factor in the theta direction is r, so then it's 1 over r partial with respect to theta in the theta direction. Then the scale factor here is r times sine theta, so you have 1 over r sine theta partially with respect to phi in the phi direction. Which again is exactly what you get, with these kind of general summaries. Let's just find it here, right? The gradient with respect to spherical coordinates, notice it's the same exact thing as what we just wrote down. So that's kind of just a tease of just kind of differential geometry, general relativity can kind of summarize these things, and the handout that's linked below is exactly this handout that I'm showing you now, if you want to have like a nice one page front and back summary of this kind of optional stuff I've been talking about.